Good morning, good afternoon, everyone. My name is Yohana Muhammad Abdurasul. I'm a student at Makerere University. I'm here to present our project, your group SWML 23, from the Department of Network, College of Computing and Information Sciences. Our project is titled as Semi-Supervised Transformer Architecture for African Mono-Narrative Classification, Mitigating Quadratic Attention Cost and OOV Token Fragmentation. So let me explain it simply. We build an AI system that can read African stories and folk tales and automatically classify them by their moral lesson. For example, whether a story is about honesty, respect, responsibility, or compassion. Our team has 3 members: Oko Victor, Herman Shematsi, and me. Our supervisor is Mr. Galiwongo Marvin. So let us now go through the content of our presentation. Here you have the content of presentation. This is let's show the structure of our presentation. We will start with an introduction where we explain the key ideas behind our work. Then we will talk about the related work, meaning what other researchers have done before us. After that, we present our problem statement, the exact problems we are trying to solve. Then our research questions and objectives, what we wanted to find out and achieve. We also present our research contributions and outputs. What we actually produced and contributed. We will explain our methodology and system architecture, how we build our system step by step. Then we go into dataset description and exploratory data analysis, how we collected and understood our data. After that, we show the model architectures we used, the AI model we trained. We then present our model evaluation results, followed by explainable AI results, showing why the models made the decisions they made. Then we cover model compression, how we made our model smaller and faster for real use. We also talk about machine learning operations, how we deploy the model online. Finally, we present our limitation, conclusion and future work, references and acknowledgement. So let us begin. Here, before we go into the technical details, let me explain the key concepts that power our system, which we call the digital elder system. Our work is built on 6 main ideas. First, natural language processing, or NLP. This is the field of AI that helps computers read and understand human language. In our case, we focus on text classification of moral narratives, especially from African oral traditions. It is what is called raw results NLP, meaning we work with very little data. Second, we use transformer models. These are the most powerful AI models for understanding text today. We specifically use models like MBAT, XLM, Roberta, Debater V3, and we tested them on our African corpus. Third, we use semi-supervised learning. This is a technique used when you have very few labeled examples. Instead of labeling all the data by hand, we use a combination of a few labels and the structure of the data itself to train the model. Fourth, we deal with a problem called self-attention complexity. The standard transformer models become very slow and heavy when the test is very long. It is called the ON squared bottleneck. To fix this, we use a model called longformer. Fifth, we tackle OOV fragmentation, which stands for out of vocabulary. This means that when African words are processed by model trained mainly on English, those words get broken into smaller, meaningless pieces, causing the model to perform badly. And sixth, we address OOD generalization out of distribution. This means our model must still work well even on text it has never seen before, even when there is a domain shift or Western bias in the original training data. We also handle document level data leakage and making sure that during training and testing, stories from the same book are not in both sets at the same time, which would make the results look artificially good. And finally, the goal of all this is cultural AI, building a digital elder system that preserves African knowledge and generates culturally grounded tomorrow stories. Here you have the related work. Now let us look at what other researchers have done before us and why their work was not enough for our specific problems. The first important paper is intention is all you need. This paper introduced the transformer model, which is the foundation of all modern AI language models. It performed very well on a translation task. However, it became impractical for very long tests because of its own n squared attention complexity. So you have something like around 8 related works. Let us proceed to the next slide. The problem statement. Let us talk about the specific problems that motivated this research. We identified 2 types of problems. The first is the domain application problem. African moral knowledge, things like folktales, proverbs, and songs, exist mainly in oral form. It has not been sufficiently digitized or structured for AI systems to use. These traditional narratives are culturally very rich, but they are in danger of being lost in modern digital ecosystems. Current AI systems are not grounded in African moral frameworks. They are built mostly on Western data and Western values. There is no scalable system, what we call a digital elder, that can preserve these stories and adapt them for modern learners. And access to authentic, culturally faithful moral content for education remains very limited. The second type is a computational problem. Our source test came from different books, written in different styles and formats, making them heterogeneous and difficult to process uniformly. The raw data contain a lot of noise, things like table of contents, metadata, page markers, and other structural clutter. Ground truth labels, meaning who decided which story belongs to which moral class, are very scarce. This makes fully supervised learning very difficult. We also face class imbalance. Some moral categories had many more examples than others, and our overall data set was small, which reduced model stability. Some narrative documents are very long, causing sequence length and translation challenges for standard models. And finally, we needed a robust pipeline that could handle all of this: cleaning, structuring, feature extraction, and low-level learning using unsupervised, semi-supervised, weak, and pure learning methods. Here you have the research questions and objectives. Based on these problems, we defined 4 research questions and 4 corresponding objectives. Our first research question was: how can African moral narratives from heterogeneous sources be cleaned, structured, and characterized into an AI-ready corpus? To answer this, our first objective was to build a reproducible pipeline to inject, clean, structure, and explore the data. With more than 25 visualizations across lexical, structural, sentiment, and thematic dimension. Our second research question was: how effective are low-level learning methods like unsupervised, semi-supervised, weak supervision, and pure learning for more narrative modeling when very few levels exist? Our second objective was to implement and evaluate all these learning strategies and find which one are best suited for our annotation setting. Our third research question was: which transformer-based architectures give the best classification performance on a cultural grounded, low resources African moral corpus? Our third objective was to train and benchmark strong transformers baselines, specifically MBAT, XLM Roberta, the Beta V3, and Longformer for category classification. And for research And our fourth research question was, how can the resulting pipeline be compressed and deployed to support the future digital elder storage generation system? The fourth objective was to apply model compression using knowledge distillation and deploy the optimized model as the foundation of the digital elder system. Here we have the research contribution and output. Now, let me highlight the key contributions and output of our research. Research contribution. Our first contribution is the creation of an African moral corpus collected from multiple sources, cleaned using a reproducible pipeline with traceable, document-level metadata, and engineered features. Our second contribution is a comprehensive exploratory data analysis with more than 25 visualizations covering lexical, structural, sentiment, and topic level patterns across entire corpus. Our third contribution is the implementation and benchmarking of low-level learning pathways, including unsupervised, semi-supervised, weak supervision, and pure learning, all tested from annotation settings. And our fourth contribution is transformer benchmarking. We trained and compared MBAT, XLM Roberta, Debata V3, and long format for cultural grounded moral classification. For the research output, our first output is an analysis-ready corpus, clean test files with structured features tables, quality checks, and before and after cleaning validation. Our second output is an EDA notebook with more than 25 visualizations showing corpus characteristics, thematic structure, and latent topic clusters. The third output is a training notebook with reproducible transformer, experiments model, comparison metrics, and our compressed deployed model. The fourth output is a digital elder foundation, a documented methodology, a deployed Streamlit application, and a roadmap for culturally conditioned folklore generation. Here we have the methodology and system architecture. Our methodology is organized into 3 layers. The first layer is data engineering. We started by collecting our data, folklores, and proverbs corpus from open access online sources like Internet Archive and Project Gutenberg. We gathered 42 books and documents on African folklores, and moral traditions. Then we performed data injections and standardization, loading the raw test file and normalizing them into a consistent format. After that, we ran pre-processing and cleaning using a rule-based Python pipeline to remove noise like table of contents, prefaces, and page markers. Finally, we perform dataset structuring, chunking the stories into smaller segments, giving us more than 300 training examples and engineering features for analysis. The second layer is analysis and learning. We run exploratory data analysis, producing more than 25 visualizations to understand the structure and patterns in the data. Then we apply unsupervised modeling, using techniques like K-means, LDA, NMF, to discover latent topics and thematic groupings without any labels. Then came low-level learning, using weak supervisions and label spreading to propagate labels to the full corpus. The third layer is output and impact. We train our transformer models, specifically XLM, ARA, and Debata, on the labeled data. And the final output is the moral narrative classifier, which serves as the foundation of the digital elder story generation system. Here you have the dataset description in EDA. How the dataset was built. We manually searched and extracted African moral narratives text from open access online sources, mainly internet, from archive, similar public domain repositories. We collected 42 books and documents covering African folklores, proverbs, and moral traditions. The content was extracted and saved as raw text files, then cleaned using our rule-based Python pipeline, removing tables of contents, preface, page markers. Then the stories were then chunked into smaller segments, giving us more than 300 training examples. We also engineered 7 features for each document: number of words, number of characters, number of sentences, average sentence length, average word length, lexical diversity, and sentiment compound score. We defined 4 moral classes: honesty, respect, responsibility, and compassion. Labels were assigned using keywords seeding, combined labels spreading, a semi-supervised technique. From the exploratory data analysis, we produced more than 25 visualizations across lexical, structural, sentiment, and thematic dimensions. We found that document lengths are highly heterogeneous, meaning some books are very short and some extremely long, showing a strong size imbalance across sources. Lexical diversity varies by source, indicating different narrative styles and repetition levels. Frequent unigrams, bigrams, and trigrams reveal recurring moral and cultural motifs. Words like African, oral tradition, young man, old woman. You have the correlation analysis showed coherent relationship among size and linguistic features. Topic and clustering analysis using LDA, NMF, K-means, hierarchical clustering, and TSNE reveal 4 latent thematic groupings, which align well with 4 moral classes. In summary, the corpus is complete and non-duplicated, and after control cleaning, it became analysis ready with meaningful thematic linguistic structured, suitable for low-level NLP modeling. Here you have the EG result and visualization. Just what all the visualization you got after during our EDA. Then here you have the data quality result. This is slide present the result of our data quality checks after features analysis. Data quality results: we checked for empty documents, we found 0, so the corpus is complete with no missing content. We checked for very short documents with less than 100 words, again 0. All documents contain substantial narrative content. We checked for duplicate text, 0. The corpus is fully unique. However, we did detect noise indicators. Specifically 8 files has table of contents, 6 had prefaces, 8 had introductions, 3 had bibliographies, and one had Gutenberg header text. After cleaning, words removal ranged from 0.12% to 3.89% per document, meaning our cleaning was controlled and conservative. We only remove structural noise, not narrative content. Here you have the unsupervised learning results. You can go through. Also, after you have the semi-supervised and the weak supervised also result. Then let us go to the model architecture and mathematical foundation. All models follow the same general flow. They take 4 or more text as input, pass it through a tokenizer, encode it with a transformer encoder, pull the representation, and output a classification into 4 more classes using Softmax layer. XLM Roberta is a multilingual encoder only model. It uses a sentence piece BPE tokenizer and 12 transformer layers with multilingual self-attention. It was our main multilingual model. Then after you have the Beta V3 uses the disentangled attention. After you have long former, MBAT, Big Bat Roberta, Electra, and BAT. Then here you have the model architecture, but for generative and clustering models. Under generating and clustering models, you have Tiny Llama, FLAN T5, GPT-2. Now for the Tiny Llama with LoRa is a decoder-only model with 1.18 billion parameters. It takes a prompt and a story title as input. It uses BPE tokenization with rotary position embeddings. We only train about 1% of the parameters using LoRa. It generates African model narratives token by token. It became our best generative model. After we have the F-Line T5 is a sec-to-sec encoder-decoder model. It takes an instruction plus a story request as input. The encoder uses self-attention and feed-forward layers, and the decoder uses cross attention. However, it significantly underperforms on our African corpus. Then you have the GPT-2, is a casual decoder with 117 million parameters. It was trained directly on our 42 native documents. It uses 12 decoder layers with causal masking. It was distilled and deployed as, that is it. Then after you have the unsupervised clustering model, you have E5 plus key means. After you have the bad topic here. Then here you have the result and discussion. Under result and discussion, you have the result, how we proceed, how we did the training setup, the validation, and the validation. Then here you have the XAI results and discussion. This is let's present our explainable AI result, meaning we looked not just at whether the models were accurate, but also at why they made the predictions they made. For MBAT, which was our best classifier with accuracy 0.934, the model predicted correctly at high rate. Its main confusion was between the respect and responsibility classes, which are semantically very similar. This is a minor and expected confusion for a best performing model. After half for Electra, the model predicted at a moderate level. It showed a tendency to collapse toward the dominant class. Honesty, but was still more stable than BAT. It showed better generalization. For BAT, it also collapsed toward the dominant class, predicting honesty too often, especially after epoch 1 confirming overfitting. After you have the XML Roberta, low accuracy of only 0.1667. Almost all predictions were wrong. The interpretation is that OOV tokenizer fragmentation severely hurt performance. When Afrikaans words are broken into meaningless sub-pieces, the model cannot understand the text. Then after you have also for debate victory so far. Then here you have the model compression, approaches and results. Now let us look about the model compression. How we made our model smaller and faster for real-world deployment. We use our best generative model, the Tiny Llama LoRa, as the baseline for compression experiments. The baseline model was 2209 megabytes in size with inference latency of 2683 milliseconds and a RHEL score of 0.1753. We tested three compression techniques. First, the dynamic int-A quantization. After the second, we have the magnitude pruning. Then after I have the third one is the knowledge distillation using the GPT-2. Here you have the compressed model selection and deployment. Based on our compression experiments, we selected the best model for deployment. We compared three compression techniques. Quantization produced Tiny Llama with about 50% size reduction, around 30 milliseconds latency, and a RHEL of approximately 0.16. Pruning produced Tiny Llama with about 60% size reduction, 25 millisecond latency, and RHEL of approximately 0.14. So so which the LoRa, which is the technique we deployed, produced tiny llama LoRa, training only about to like 1% of the 1.1 billion parameters, saving about 80% trainable parameters, with a latency of just 13 milliseconds of root L of 0.1753, the best quality score. So we selected Tiny Llama LoRa as a deployed model. We built a Streamlit web application called Digital Elder. We can see the screenshot of this on this slide. The application allows users to generate African moral stories by providing a story direction. For example, write a story about kindness between two girls. The Digital Elder system to generate the digital system then generates a culturally grounded moral narratives. The deployed model is available online at the link shown on this slide. Then here you have the technical limitation. Like any research project, our work has limitations, and we want to be transparent about them. Data limitation. First, our data set is small, 42 books with around 300 training examples. This is insufficient for stable deep learning, especially for large transformers model. Our practical suggestion for future works is to collect more African folk tales from Uganda, Chad, and DRC, and to digitize oral sources. Second, you have class imbalance. Honesty is the dominant class, while respect and responsibility are underrepresented. Now for the system limitation, you have our corporate is mainly in English. There is no real multilingual support. African languages like Luganda, Arabic, or French are not included. Here we have our conclusion and future work. Now for the conclusion and future work, we successfully curated a clean and structured African moral narrative dataset from heterogeneous sources. You completed a full exploratory data analysis with more than 25 visualizations revealing lexical, thematic, and structural patterns. Our best classifier was MBAT, achieving an accuracy of 0.935, and macro F1 of 0.801. Our best generative model was Tiny Llama, which we used to deploy it. Then for the future plan, we plan to expand the corpus with Luganda, Arabic, and French factors from Uganda, Chad, and DRC to address the small data set and English-only limitations. We plan to involve cultural experts and linguists for annotations, quality, and to fix class imbalance using SMOD. For the references on this slide, we list the academic papers and works that inform our research, so you can have our different references here. Then here in our acknowledgement, finally we would like to express our sincere gratitude. We thank our supervisor, Dr. Gwalengo Marvin, from the Department of Computer Science, College of Computing and Information Sciences at Makerere University, for this academic guidance, feedback, and continued direction throughout this research. We also extend our gratitude to Makerere University for providing the academic environment and resources that supported this work, and we thank our teammates and colleagues for their collaboration in data preparation, model training, analysis, and experimentation. Thank you very much for your attention. We are happy to take any questions.